Okay, nitration mechanisms. I have nitric acid and sulfuric acid. And nitric acid looks like this. A nitrogen with a double bonded oxygen, an OH, and a negatively charged oxygen. And what's going to happen here is I have an acidic proton, which comes from the sulfuric acid, and that is going to attach onto the nitric acid. I could also write it like this, because that's where that hydrogen comes from that I need to attach onto the nitric acid, but really I could just write an H+, it's the same thing. So the electron pair from the OH is going to attack that acidic proton, and it's going to look like this. Giving water, which is a very good leaving group. And so what's going to happen now is the negative charge from the electron is going to turn into a double bond and kick off the leaving group, the water. And it's going to look like this. And and I just realized I forgot to write my positive charges on the nitrogen. Oops. Okay, so at this point is when I can actually start the mechanism. So I'm going to redraw my aromatic ring, and my nucleophile is going to attack the electrophile. The electrophile is the nitrogen because oxygen is more electronegative than nitrogen, making nitrogen electrophilic. So the pi bond from the aromatic ring is going to attack the nitrogen, and because I can't break the octet rule, I'm going to kick off one of these double bonds and attach it to the oxygen. So that's going to look like this. Our alkene again, or our aromatic ring again, except now we have a sigma complex, the O negative, and then we're going to use a base, so water, and that is going to deprotonate the aromatic ring, and then what's going to happen here is the electrons are going to grab onto the hydrogen, and then the bond from the hydrogen is going to add on to the aromatic ring, making it an aromatic ring again. And so that's going to look like this. And this right here is called a nitro group. And that is our final answer.